Assalamu alaikum. Ashhadu an la ilaha illallah wahdahu la sharika lah. I'd like to thank the organizers of MSLM 26 for giving me the opportunity to present on this topic. So, first of all, when often people hear nuclear physics, the first thing that comes to mind is a bomb. But this talk, you join me in a journey where you realize that the applications of nuclear physics and atomic physics are so much life-saving as we imagined. As we can't imagine. So those who are in medicine and oncology for that matter, radiation science, the whole of radiation science comes from the atom and the nucleus. So to begin with, I'd like to introduce a basic structure of the atom. So the atom is composed of three particles: the electron, the proton, and the neutron. The electron is negatively charged, while the proton is positively charged, and the neutron has no charge. The neutron and the proton reside in the nucleus. And the interactions between these three particles are what produce all the radiations used in radiation science. And I use this verse because, thanks to Dr. Nusrat Sahiba for her presentation, the electrons are going around the nucleus like the planets are going around the sun. And there is a balance. And every particle in the universe wants to be in the ground state of rest. But in nuclear and atomic physics, we create imbalance and allow nature to take its course. So when you create an imbalance, you disrupt the nucleus of the atom. And the atom wants to come into the ground state. It is this recreation of balance is what leads to the emission of radiations. And we utilize these radiations to diagnose diseases as well as cancer. So there are so many radiations that we can get, but a couple of them are listed here. We have the alpha rays, which are the heavier particles. Then we have the beta, which are like the electron. And then we have gamma and X-rays. Gamma and X-rays are both electromagnetic, but X-rays have low energy, and they are produced at the atomic scale. So we say they are in the keV range of energy. The gamma rays are produced in the interaction between the neutrons and the protons. So they are in the MeV energy range, so they have more energy than the X-rays. And then we have neutrons, of course, they come from the nucleus of the atom. Each of these radiation has its purpose. So to start with, let me look at the interactions at the atomic scale. So you have an electron, you excite the electron at high energy, you impinge it on a target. It can be any element, but mostly we use tungsten in diagnostic radiology. This electron beam impinge a target of a tungsten, disrupting the structure of tungsten, removing other electrons. And other electrons want to come up to the ground state. Doing that, they emit X-rays. And these X-rays are harnessed, and they are used to diagnose people for scans. And Alan Cormack and Hansfield discovered that we could actually have a 3D scan using X-rays. And they won the Nobel Prize in 1979 at the same time that Abdul Salam won his Nobel Prize. And they discovered that they could use X-rays, which give 2D image, to form 3D image. So this is still application of X-rays. But the production of X-rays is still fundamental physics. The second one, this is nuclear physics, diagnostics of cancer and other diseases in nuclear physics. So we use something called the MRI. The MRI originally is NMR, which is nuclear magnetic resonance. The human body is composed of water, which is 2 molecules of hydrogen and 1 molecule of oxygen. And hydrogen is just 1 proton. So we call hydrogen a proton, which is positively charged. So what you do is that because the proton is positively charged, it is influenced by an electromagnetic force or a magnet. So what you do is that if you place a human being in an external magnetic field, MRI, what it does is that it disrupts the normal orientation of the protons. They reorient based on the alignment of the magnetic because the south and north pole. So what you do is you give a small pulse of radio frequency to disrupt the normal balance, and it has to rebalance itself. It then emits radiation again, and this radiation, which is still in the radio frequency range, is harnessed and is used in medicine to reconstruct the image because it contains the information about the function of that tissue that you are imaging. What I want to go here is the PET, then I'll talk about the SPECT. The PET is interesting because it confirmed the chronic verse that Alex created everything in pairs. So you have positron emission tomography. What happened is that we have matter and we have antimatter. The matter of the electron is what we know every day. The antimatter to the electron is the positron. So electron is negatively charged, but the positron is a positive electron. It's not proton. So what happens is that when you have a positron, it doesn't stay for long. So it has to find an electron and pair with it and actually annihilate, right? So if I would die and you are not married, you are possibly looking for a spouse. That's annihilation, actually. So when you have a positron radionuclide, it's injected into the body. It emits a positron. The positron look for an electron and annihilate. They form a back-to-back gamma ray. The rest mass of an electron is 511 keV. Don't worry about the energy, it's 511. The two of them has to give you about 1.022 keV. The energy of the gamma ray should be 511, 511. They have to be back-to-back for momentum conservation. Don't worry about that. And charge conservation. But what happens is that you have detectors around the PET scan. And they have to detect these gamma rays simultaneously because if there are two gamma rays come at the same time, they have to be detected at the same time because they travel at the speed of light. And this information is used to reconstruct the image of a tumor. And the PET has the specialties that is able to tell you the function of the tumor, how aggressive the tumor is. And with the SPECT uses, unlike the PET, which uses two gamma rays, the SPECT uses a single gamma ray emitter. So what is that? Is that it's still a radionuclide. You inject into the body, but it will decay naturally and emit a gamma ray. The gamma ray is detected by something called a gamma camera, but again, it's a gamma detector. And it brings the information of the location of the radionuclide. And this can again be reconstructed into an image for diagnosis. Now, I've talked a lot about the diagnosis because you have to, in radiation oncology, you have to know that, first of all, can we see the cancer? Second, of course, can we understand it? And now, can we treat it? How do we treat it? That's where you have to use radiation therapy. And I explained how X-rays are produced. X-rays can be produced in a range of energies. So we have soft X-rays, we have hard X-rays. So we can produce X-ray for diagnostic imaging, which of course will use low energies. We can increase the energy of an X-ray by increasing the acceleration energy of the electrons that hit a target. So they produce more energy because some of them interact with the electrons in the atomic shell. Others go to interact with the field of the nucleus. And the field of the nucleus is positive. So it tries to slow down the negative electron charges. So there's a continuous loss of energy, which we call Bremsstrahlung. And all these energies are used and harnessed well at moderate measurement to treat cancer. Another popular and advanced technology is what we call the proton therapy. So the proton therapy is using protons. So you accelerate a proton, but this time around, you're not producing X-ray. What you do is that the proton has something you call the Bragg peak. When you accelerate a proton, it loses energy slowly, And at some point, it loses all of its energy at once, which means that the proton spare most of the normal tissues and focus much on the tumor if the target is right. Because in all this radiation therapy, you are treating the tumor as well as the cancer, but you want to be as localized as possible to treat the tumor away and sparing the normal tissue. That's why you have to even give the radiation in doses so that the normal cells have time to repair while the tumor, are dying continuously. So what happens is that when protons are charged particles like electrons, but they are positively charged and they are heavier than electrons. So once you accelerate them, because they are heavier, they travel slowly as compared to an electron because of momentum effect. So as they travel through the tissue, they will lose energy slowly, but if your target is right, within the shortest time, they, release all its energy. And it's very good in tumor therapy. And I think it's been classified one of the safest, if not the safest, in radiation oncology. And this would be my last slide. So I just wanted to let you know that neutron therapy is coming up. But the thing about neutron is that it has no charge. So when it enters the bodies, it's just going to the nucleus itself. And a neutron-nucleus interaction can lead to the disintegration of the nucleus as well, which can lead to a lot of them, which can have more effect on the tissue as compared to proton and X-rays, because we can handle them because we know how to do that. So, but the takeaway home here is that in my first slide, I said, oh Lord, increase me knowledge. I didn't mention that because I wanted to get the journey first. In the beginning, scientists were not studying the atom to cure cancer. It was to ponder over the creation of Allah. But in that pondering, we're able to invent technologies that are applied and used for the betterment of mankind. So if, as scientists, I'll quote one sentence, I don't remember his name, but he says that the things we see in science are not because that's what we are looking for, because they are possible to be seen. So if you are doing science, do a good science and ponder over the creation of Allah Almighty. You should have good intention. And inshallah, we can always save mankind. Jazakallah. Assalamu alaikum wa barakatuh.